Here we are in the latest video. I'm going to give you a little tour of what area we're in. So we got a little bike here. We got some access to light. Not really the best of roofs. And then a whole bunch of empty jugs. I don't know what's going on in this place, but it's a covered location for us to be working in. We're going to cover two main ideas. We're going to cover Dalton's law of partial pressures, and we're going to talk about effusion, which is different from effusion, which is different from diffusion. All right, so let's get into Dalton's law of partial pressures. Partial pressures, that's exactly what it sounds like. It's going to be parts. And here's Dalton's law of partial pressures. It's basically that the total pressure of a system is equal to the partial pressures that each gas provides to the system. So we have the P total, which is equal to the pressure of one gas plus the pressure of a second gas plus the pressure of third plus whatever number we need. And this is all because of the idea that we discussed earlier that gases act independently. So they're all doing the same thing. They're all bouncing around, and then because their kinetic energies are equal, they're all providing the same pressure. So we just need to add them all together and get the total pressure of the system. Now, where this is primarily used, and we're going to blah 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 blah. Our calculation lab that we did, we actually had a mixture of two gases in the eudiometer tube. It was hydrogen and water. So this connects that activity to the idea of partial pressures. So the total pressure, that's what we use to calculate R. That was equal to the pressure caused by hydrogen and the pressure from water. Because water has a vapor pressure just like every other liquid, and some of the water evaporated inside the eudiometer. And we're going to actually calculate R again, but minusing the water vapor pressure, and we're going to see if we get closer to R. So our calculations were a little bit off because there's extra pressure there. So our pressure, because of the hydrogen, is actually a little bit lower. Now, the second one that we're going to get into is effusion. So, let me just back up. So, don't worry about this. That was a little mistake. I didn't want to talk about the rate, but effusion is generally the gas passing through a tiny little opening. So you gotta imagine an empty chamber, and then a tiny, small opening, because obviously if it's a big opening, the gas would just go rushing right in. But a small opening would let little gas particles in at a time through the random motion, bouncing around. Eventually one would be on the right trajectory and make it through into the evacuated chamber. Now, that's effusion, which is different from diffusion. And there's a law associated with the rate of effusion. It's Graham's law of effusion. And that says that the rate of effusion is related to the molar mass of a gas. But it's not directly, it's inversely, which gets to the idea that it's obviously going to be related to velocity. The faster it's moving, the more likely it's going to be bouncing around and get to that tiny little opening. Well, velocity is related to mass. So he found that the rate of effusion of a gas is inversely proportional to the molar mass of the gas. And we can make a ratio of two gases. So we have two gases and we want to compare the rate of effusion, take the rate of gas A, the rate of gas B, and the rate of B is up here in the top. So B is on the bottom, but now it's on top. That's where the molar mass goes. And the molar mass of A would go on the bottom. So a quick little example is ammonia, NH3, and hydrochloric acid, HCl. So we can compare the effusion rates if NH3 is smaller than HCl, it's almost about half, right? Well, NH3 should go faster. We have a tube which is not empty, so this is not empty. If we have a tube with hydrochloric acid going in on one end, a tube of ammonia going in on the other end, and we compare, well, the rate of the gases, we can since we're not going to be able to measure the speed, we can compare the distance. the faster a gas moves, and then the more distance it should be able to cover in a given amount of time. So we have the distance of NH3 over the distance of HCl. So since NH3 is smaller, it should move faster. This should give us a larger than 1 ratio. So molar mass inverse. So molar mass HCl goes on top, molar mass of NH3 goes on the bottom, but it's the square root. So I'm not sure if I mentioned that, but it's the inverse molar mass in the square root. And then, so we get the 17 on the bottom, the 36.5 on top. We calculate that, and it comes out to 1.5. But if we were to do this, and I've tried doing this in class a whole bunch of times, and it doesn't really work very well, so maybe I'll show a video of it in class on Monday. But we do this with air in the tube, and it comes out to less than 1.5. With the ratio of the distance covered by NH3 versus the distance covered by HCl comes out to less than 1.5, which means that the rate of HCl is faster than we would expect. So the big question I want to ask you and to answer in the assessment is, why do you think that is? So that's it for this weekend, this video, and if you can even imagine where we might be, I'd be impressed. So see you Monday.